So I ran again another trade show. I was at Exponential in Dallas and ran across the Qualcomm booth. And I had heard about stuff for a while because they were doing their Snapdragon. That's all my garbage was away.
No, this is all good. I should have brought more props. I always forget. I think, oh, I got everything I need, and then I go, I'm like, I should have brought something more. But
so I was excited because of the Snapdragon, and Snapdragon was going to be. So all the technology I saw in all the drones, you had the ability to send 4K video, and you had sense and avoid, and you had what is it like? It would map out the area that it traveled, so if it lost connection, it could still follow that back. All that was in this little teeny board, and they were going to blast that board into all kinds of people selling drones. So you would have all kinds of options. Just happened to be using Qualcomm stuff. So super excited to talk to them about that and see what was up. And after talking to one of the individuals at the trade show, eventually got in contact with this gentleman. And so I will pass it on to Chad.
All right.
And he will warn you.
All right.
Thank you, sir.
All right. Well, thanks, Mark and Wing, for having me. My name's Chad Sweet. I lead robotics R&D at Qualcomm Research here in San Diego. So how many people here are familiar with Qualcomm? Most people? Okay. All right. Well, you never know.
It's a stadium, right?
That's right. I do get asked. That's right. I do get asked, what it's like working at the stadium. I don't work at the stadium. So for those that have smartphones, which is probably everybody, we probably have some component in that smartphone in your pocket. Some of them way, way more than others. Many of the Android phones, we have lots of the components, like lots of, 10, 12, 15 of the chips. And some of the, non-Android ones, we have a pretty good chunk of technology in there as well. Qualcomm Research, our responsibility is to look for the next couple of years of technology and help position Qualcomm to take advantage of that. And so we've, for the last few years, been looking at aerial robotics, or robotics in general, but aerial robotics and drones as one of the areas that Qualcomm should be a part of. There are a few other things that we're looking at as well, actually a lot of different things, probably 20 different things, but here's the big ones. Of course, 5G technology, if you're familiar with 4G or LTE or gigabit LTE, 5G is next, and we've got a huge effort in trying to make that happen, of which, interestingly, there is a component that are referred to as mission critical, and we'll talk a bit about that later, and that mission critical 5G is directly applicable to aerial robotics and making sure that you're connected always to all the things that are going to be flying around in the world, rolling around in the world autonomously without people. So one of the ways we manifest that technology is what's referred to as our Snapdragon processors. This is the full thing that fits inside your smartphone, and it packs everything into these absolutely tiny little packages. I think this one is, this is the Snapdragon 820, which you'd find in the Samsung Galaxy S7, as well as some other ones, and it's 14 by 14 millimeters. And so the big role of my project is to take that Snapdragon processor and make it applicable to robotics. So repurpose all the various components to be used for robotics. And to do that, we've taken things like, this is on a smartphone, this is the low power sensor DSP. We made that the high power DSP. We turned all the clocks all the way up and used that to run a flight controller. We've taken the front end, which referred to as the image signal processor for video, and repurposed it so it could do 4 cameras simultaneously. As Mark was talking about, the 4K video, sensors, stereo depth sensors for sense and avoid, as well as tracking for better stabilization, or for better localization, which can be used then for stabilizing the vehicle and preventing the GPS flyaways that Mark was talking about. So, well, yeah, and so actually, so the rest of this talk, as we get into the details, is really about how to make, the goal being a single operator to do the video and do the piloting. It really, the computer does the onboard piloting. That's the intent. Because actually, from my experience as well, I was just out filming my 10-year-old on a bike in a canyon and trying to do both, keep him in the field of view and follow him while running behind him. And I crashed into a tree, and then that was a whole ordeal where my son thought I was a complete idiot climbing up in a tree, drones hanging over the water, and the whole bit. And so, so this technology, I think, I'd agree. Actually, it's not there. It's not ready. Even on the most advanced stuff out there, like a Phantom 4 Pro, a DJI Phantom 4 Pro. Really, they've got like the forward field of view covered, and the rest is guesswork as to whether it's going to run into something or not. And so, we think this technology really will, as it advances, improve the accessibility such that it makes it easier and easier for more people to be able to actually get great video and do other surveying tasks. So I don't know. I know some folks were talking in the DIY. I don't know, DIY space. How many folks in here would consider yourselves like a software developer? Okay, we have one. All right. I'll try and I'll glance over that and kind of focus on how some of this technology will be useful for videography. So one of the main techniques of robotics or autonomous robotics is referred to as SLAM, or simultaneous location and mapping. And one of the technologies that we're working on is referred to as visual inertial odometry, or VIO. And what that does is provide this centimeter level accuracy localization. And that can help for either indoor navigation, so let's say you're filming in a stadium or like a basketball court, something like that, or help stabilize beyond what GPS could do and help remove some of the errors that you might find in GPS. So GPS flyaways are a pretty common phenomena. This, if you're outdoors and let's say you're stabilized, in the centimeter level, you can barely see it move. In fact, if you looking at it, almost looks like it's just hanging there. If it weren't making noise, you would think it's just fixed. It's stabilized so well. This can help you much easier, create video and then also do the same sort of thing indoors. Here's an overview of how that technology works. Effectively, it's taking that tracking camera I referred to on the architecture slide, working with the features. You'll start to see these features in a second. I'll wait, let it run for a second. Okay, so these features, the feature points you see, those are what's being tracked, and those are tracked in the pixel space. So the software is tracking those using pixels, like XY coordinates on the 2D image. And then it's using the IMU, or the inertial measurement unit, the accelerometer, specifically to convert those pixels into real world coordinates. And that is actually building out a map of these pixels, which the software can then use to localize itself. And so here, this is this showing an extreme use case where they're running around a building, get on a bike, get on a skateboard, go around, and come back, and it says that it came back within, I think, 0.6 meters after a 600-meter loop, showing how well that this localization technique can use. And so we end up using this for all sorts of indoor navigation. So one of the interesting things, one of the interesting use cases we're targeting about that for aerial robotics is security. So there's a lot of folks that want to put drones in warehouses and put drones in all sorts of buildings, because in some ways it's a simpler problem to solve, a little bit, not always. On the ground you have to avoid obstacles and things that move, and in the air you can avoid all that stuff. But depending on how the building's configured, you might be able to move around much easier and much quicker with a drone and actually do surveillance. And so you'd want to be able to automate that as much as possible. And so here's a very similar thing, just showing it work outdoors. You see the features are being tracked. The other, some other benefits of this is that you can actually fly close to tall buildings, where often that's typically a use case where GPS will fail, and you don't want your vehicle to get out of control when flying really close to a building, because it could smash into a building. I've seen it happen on our campus with one of the vehicles that was talked about in the previous talk. The very high-level executive at that company took it off and put it into mode, and the GPS got out of control, and it slammed straight into a building. So these are the types of things that this technology helps enable. Some of the cameras we can use up front for this obstacle avoidance and mapping type technology, and this technique is referred to as depth from stereo, where you take a camera on the left, camera on the right, and you find common pixels or common features in the images between those two camera images. And from there, once you find them, you know the calibration parameters of your cameras, and you can actually use fairly basic trigonometry to compute the depth of that feature off in the distance. And so from there you get this depth map, in which that's what's shown here is this, these are depth values using color codes. The darker blue it is, the further away it is, and the lighter blue or green, the closer it is. And once you have that depth map, you can see, well, you know, there's something there that I don't want to run into. And in the area use case like this, it's fairly straightforward once you have the depth information. Often, if there's anything there, you can just stop, which is kind of the primary thing. Something's there, stop, don't run into it. And sometimes that's actually good enough. Now, we'll show some more complex stuff in a minute, but here's how that might be, you know, realized. This is at our office in Philadelphia. They're flying out there. And this is why I wish I brought a prop to show how actually small we can build this when you integrate everything into this small package. This is a 210 millimeter frame that can a 210 millimeter frame drone that weighs about 195 grams that can do 4K video and sense and avoid and all this autonomous capability, which is really fun to see. And you know, you of course get increased flight time the larger the vehicle, and that can be very, very important. But the smaller it is, and the counterpoint is it's safer. I mean, you know, you know, that's one of the trade-offs, especially as you're getting new. You know, when counting the trade-off, one of the things, if folks are kind of getting into flying, we make everybody buy these Hubsons, these $40 Hubsons, and you got to get good at flying that thing around the building and around the office before we let you keep moving up the scale, which is one of those interesting counterpoints, especially to just flying my drone into a tree and almost losing it. I did recover it. Is that, you know, you take the Part 107 test, and like nowhere in there does that make you qualified to fly it in any way. It's like all you know is where not to fly it, and that's it. And then kind of. The app is still just better anyway. But yeah, so this is how that might get realized. The drone's being commanded forward, and it's flying. All the user's doing is telling it go forward, and the drone finds its way through the trees just by using the algorithms not to run into each other. No, so it showed you, okay, you can do basic things like avoid trees and stuff, but what if you want to do more? What if you actually want it to navigate through a building, collect video, follow people while avoiding other people, follow one person while avoiding another to kind of capture this video? You need to build out more complex SLAM techniques. And so for here, what I'm going to show is, well, an architecture that goes through and creates ultimately this map based on voxels. So to create these voxels are these 8-centimeter cubes you see represented here. All of the processing here is actually done on the drone, but we're using a visualizer on a PC. And in the upper left, you see the first-person view from the drone. Bottom left, you see the third-person view, and then this is what the SLAM system internal to the drone thinks it's actually doing. So we create these 8-centimeter cube voxels, and they're color-coded for altitude in this case. And we use the depth from stereo, the stereo camera to get the depth map. We use the VIO for localization. You know where you are, and you know this depth map projected out there. You can then start to fill out volumetric areas out in the space in front of you that map your environment. So you can see we had this archway and so forth, and so we've created this archway, and so we've set this blue pin here is the home location. And so somebody's trying to fly the drone into the arch, and it's saying, oh, okay, there's something there, I'm not going to do it. So on board in here is this memory. It's remembered the environment. Now it can really only fill this out in the direction it's pointing. So if something were to change behind it, in this case it actually wouldn't know, and it could make a mistake. But then we're going to say, okay, go home, go back to your location. It computes a path, and then this pink line created represents the path, and the vehicle flies home, comes through the arch, and makes it back safely by not running into things. And so This technology, this is not really deployed in any commercial or vehicle that you can find today at all, but we think these are the types of things that will make this a lot safer and a lot easier to use going forward, especially for the aerial photography case, indoors and outdoors, doing it safely with, with hopefully maximizing ease of use. And then for fun, I know this is aerial robotics conference, but you can kind of see how it might work. So we've extended this to actually work in our building. This is our building in Sorrento Valley, the Qualcomm Research Center in Sorrento Valley, and you can see a very similar system working where we've loaded an indoor map, put it on a ground robot because it would be it wouldn't be safe and pretty difficult to actually test it on a drone today going through our building. But you can see that the robot can actually navigate in a similar fashion on a much larger scale. So are any folks considering using deep learning in their video applications at all, or familiar with that? Yeah? Okay, cool. So deep learning is one of these technologies that over the last couple of years has absolutely exploded. And in general, in a simplistic sense, what it allows is for classification. We're actually, in our video pipeline on the smartphones, we're now using deep learning to try and guess what kind of scene it is. Oh, indoor, classroom, and you set the filters appropriately. So it's doing all this classification. One of the things that you can use it for, actually on your camera's autofocus, you might see it start to recognize faces and put squares around the faces. That's very likely a deep learning technique, classifying these as faces and then setting autofocus appropriately to do that. And so that's some of the autonomous stuff that you can build out in that way. In this case, what we've done is we put it in kind of this mocked up environment. We're running our deep learning system on board, and what it's doing is we trained it to recognize, and everything in deep learning is done through training. You set up these models and they represent these neural networks, and you train the networks on various classes. So in this case, we've classified drones, pallets, people, barrels, ladders. Let's see, let me know if you see anything else. But construction signs. There we go. There's another one. And we had it fly around. So we start out flying around 2 or 3 meters per second. And again, this is the onboard view, so like what you call FPV or first-person view, but with the classification system running on the FPV. And so we start around 2 meters per second, and then in a minute we crank it up to 7 meters per second and actually show the thing moving. Now these drones, we had a little swarm of drones, 3 of them flying in a pattern. They're all flying the same pattern, and it's done fully autonomously. So there's actually nobody controlling the vehicle at all. Yes, sir.
Is each drone individually mapping its own internal VIO that they're not speaking to each other at all? There's no connection with
Correct.
multiple drones?
That's true, except there is one little, to make them do the exact same thing, they each have a trajectory loaded, so kind of like a waypoint path. They all have the same waypoint all have the same waypoints programmed into it. And then they're all using, every so often you'll see a tag on the floor, and they use that to align so they all know the exact same reference position, but their VIO mapping is all done uniquely and independently. But you need to kind of sync them together in a way. And so we did that through timing, and then we have one visual marker in there that says, oh, this is where kind of the, home location is or whatever. But other than that, they are going all independently. But you can see as we spun it up, the system still worked. And my favorite thing is, is the fact that it can recognize other drones. When we got going with this, the FAA is saying, oh, drones are dangerous and drones are really bad. And one of the things they said was drones will never be able to, or aircraft would never be able to detect another aircraft using vision. You need these big ADS-B transceivers and so on and so forth. But here we are now, just a couple years later, actually doing it live and for real. So it's kind of fun to see all that come together. And so, what are we doing in San Diego? We have a warehouse in Sorrento Valley where we have motion capture cameras that help us test the accuracy of our SLAM system and our flight system in general. Has anybody had a chance to use a motion capture system in any of their work? Yeah? Oh, okay, cool. So what this does is you've got these little IR reflective balls on the object, in this case a drone, that you're trying to track. and it has these cameras. Let's see if I can, you can see kind of on these tripods here, these cameras, and what they're doing is they're beaming IR and reading back the reflections, and from there they figure out exactly to like sub-centimeter accuracy, or really millimeter level accuracy, where the object is in the environment. So as our system, like our VIO system, as it's reporting what it's doing, we can actually test that very, very accurately in our warehouse. The second thing is, now we're in an urban environment, and we're in or what would this be called? I don't know, suburban environment, and we're within Miramar Marine Corps Air Station's Class B airspace. And so we've had to get this, it was Section 333, now I think it's just a COA. But we have an exemption from the FAA to be able to fly there and do our outdoor testing as well. And so, which is kind of fun, we call into Miramar on the tower, and we're Qualcomm 1, and we go off and fly the drones. And you get these funny reactions because they're like, even though we have to submit like 48 hours in advance we're coming, like they're never really, like I think they're always surprised that we actually call in. So, because we're this, it's this big, the drone's this big, and like an Osprey will fly overhead. Like it could never even get into the water. Like there's no way it could actually have enough thrust to get into the airstream of an Osprey, but you got to do it. It's the way it's set up these days. So,
How hard are you guys flying there?
yeah, oh yeah, there's a limit. It used to be 200. I think we're at 400 feet now. But yeah, we haven't actually requested to go beyond 400 feet. At this point, I don't know if it would get us anything anyway. And so, since we're Qualcomm, we've got to bring in the communications component, and we, as I mentioned earlier, we are looking at how these things affect your traditional ground terrestrial networks, or LTE networks, like you'd use with Verizon or AT&T or T-Mobile or Sprint. And we look at this as, we'd really like to help enable the beyond line of sight activities. And as you get out of the range of these controllers, some of them have, multi-kilometer range, the point-to-point controllers, but still, that's typically within your visual line of sight. To start moving beyond to enable these things like deliveries, or maybe some bridge inspections and stuff, or railway inspections, or other things that are agriculture and all that, that might require, beyond what you could do with controllers and beyond what you could actually see. We think cellular is going to be a big part of that, where you're actually putting a little dongle on there and letting the vehicle fly, and watching it over your laptop, and on a map or something like that, which we have prototyped that full system. But to do that, we have to actually make sure that the system can perform as intended. And what's interesting about that is that the radio up there can see a lot of, we have a video here, it's overly dramatic marketing video, but as the vehicle goes up, the modem can see all the base stations in the area for miles and miles and not miles. Coverage improves a lot due to free space propagation. It improves so much that depending on what you're doing, you can actually be harming a lot of the traffic on the ground, which is why the first commercial thing to go out was a Verizon Sierra wireless dongle, and that's capped at a very low data rate, like 700 kilobits per second or so. And the reason is, as the vehicle goes up, you can see a lot of base stations. That means when you start transmitting at high power or high bandwidth, they can all see you. So you don't look like one user in the air, you actually look like 15 or 20 different users in the air. And so the carriers are very concerned about that, and we're working with them to help mitigate that, because these things can actually take quite a bit of time, many, many years to work through the whole system, and make it out in such a way that, of course, that the goal being everybody's got drones that are fully autonomous in the air, going and doing their business, and safely and effectively and monitored and the whole bit. And then, of course, where is it going to go? More sensors, more processing on board, more autonomy, more communications. And I think you'll see all that play out in this industry, and you'll see, hopefully it gets easier to use. I imagine either, the smartphone case won't be that you're actually controlling it via, like your control sticks via smartphone. You just say, oh, go do your thing, and 20 minutes later it comes back and it's done what it was supposed to do, and it's a successful endeavor. And so that's what I have. Any questions or any more questions?
So, this technology that you're creating, who do you plan to sell to? Are you going to make drones, or are you going to sell it to drone manufacturers?
Yeah, so Qualcomm really sells chips,
Right.
chips and software, and we see this is an interesting market for those chips. And so we work with drone OEMs today. I should have kind of brought that in a bit. There are products on the market, not at the kind of level of what you're probably trying to do, but there's something called the hover camera, which you can find at the Apple Store. Very consumer friendly. You just kind of unfold it and you hold it out and it flies, and you can wave and it'll take a picture. That uses our technology. There's a number of different other Chinese ODMs that are doing stuff. There's one called Zero Tech, this Dobby. It's a very little, cheap drone. But the idea has always been about compressing as much technology into as small of a package as possible to make it as consumer friendly as possible.
What's really needed out there is a competitor to Lightbridge.
Yeah, I agree with you.
You deliver that to the drone manufacturers, and then we'll have a new one.
Yeah, that's right. I couldn't agree more, actually. That is something that we're actively working on. The thing is, we're trying to not that different from what Lightbridge has done. Lightbridge has taken somewhat of a Wi-Fi stack and repurposed it for this use case. That's something we have a lot of Wi-Fi silicon. We make a lot of Wi-Fi chips.
That's why I brought it up.
Yeah.
I know you have that expertise.
We do.
I don't understand why you haven't pursued that. That's why Autel and 3DR and all these others unique, they're still using Wi-Fi, and compared to Lightbridge, it sucks.
I know, it does. I'm with you. And it's something we're working on. I don't have a formal announcement or anything, but it is something we're looking at seriously. And I hope we can do a lot more, because that is one thing that DJI has done a very, very nice job doing. Yes?
Is that SLAM technology what they're using for autonomous cars right now that they're trying to roll out?
Yeah, it's very similar. The requirements are a bit different. Of course, we do a lot of stuff indoors, and you don't drive your car indoors. But on the flip side, they're going very, very fast, and we're not, relatively. Even at 7 meters per second, a car's going, 100 meters per second, 60, 100 meters per second, or at least it can. And the safety profile is much, much different. We can just stop. We can shut off. Worst case scenario, we can just say, stop and drop. And a car can't do that. It can't slam on the brakes. It could be more dangerous to slam on the brakes. And certainly, so there are, but yes, in essence, the core fundamentals are very similar. Yes.
Could you talk briefly about the overhead with the deep learning in terms of processor and memory and training time?
Oh, so. In that demo, we were running the deep learning classification at 12 frames per second, or 12 hertz. That was mostly done on the GPU, so we were probably fully utilizing the GPU at 12 hertz. That was actually on the original Snapdragon flight board. The training time, I don't know off the top of my head. If I were to guess, it would be in the couple hours range, but it's all, anything in deep learning, regardless of what it takes on the runtime, what it takes on the training time, it all comes up, the bulk of the effort, the bulk of the concern, and what everybody worries about is getting annotated data. And where you get the data and how you annotate it, and how you make that happen. Because that's what these training engines actually need, is high quality annotated data.
So you create that annotation, or you recruit that from other sources?
So we do both. We have a workflow for creating the annotated data, that involves yeah, we have a workflow that we use a third-party source to annotate the data. How about how about that? Yeah. Yeah.
How far out are you from being able to start selling these things to the drone manufacturers?
Oh, that's a good question. Most of this is kind of working its way through now, in various shapes and forms. Not in the, so all of them have different use cases. The security stuff I think is very interesting. That's something that indoor autonomous drones for your house is something. Actually, you can look. In January, we announced we were working some with Alarm.com, which is like a DIY security company. Actually, they're more than DIY. I think they sell to a lot of different OEMs as well. Working with them on putting a drone in your house and doing this mapping sort of thing. And then in the consumer space, we've got a couple of good customers that are doing follow-on products and stuff with what they've built in the past. And so all of it's got some relevance in the OEMs, to the OEMs. What did I say? One of them was a little bit further out, but it's all within the next couple of years.
That interests me because the one video shows where it's going through the column.
Yeah.
So I was at, I think it was NAB, it was not 3 years ago.
Yeah.
When Qualcomm did that demo, I was like, oh, I can't wait, it's gonna be awesome.
Yeah.
So what's going on? Every trade show they had Qualcomm, but it was a different division who like, we don't talk to that. We don't know those things.
Yeah.
So I was like, when is this stuff gonna happen? It's taking a while.
It takes
We
way
don't
more.
want it to take a while.
Yeah, no. We're kind of at the front end of the, what we do in the labs, it can take many years sometimes, which is really frustrating. You think, hey, it's working, it's done, or it's, but it's, you have to build products and hardware and 10 different revs and, build the supply chain and get it out the door, and it takes a while.
Do you foresee 5G having lower latency than 4G to enable drones to be controlled?
Yeah, that's exactly that mission critical arm of 5G, and the idea there is sub-millisecond latency.
Part of the goal,
That's part of the goal for 5G. Yeah, and so you could actually fly by 5G would be the intent.
yeah.
You see 5G as, you see needing to wait for 5G before Wi-Fi communication with the drone can be left behind? Or-
No, I mean we think we've kind of proven that LTE works. If you can kind of limit the data rate, that would be the one condition at this point. Not blasting 4K video, when you're up at high altitude. That would be the one condition where you could run into it. Would work, but you'd actually be, the carriers would be upset. Your provider would be upset.
Or you'd have to focus it onto one.
Yeah, with beamforming and so on and so forth, that's possible, and that would be an LTE advanced feature that's there, but it's not really deployed yet that widely.
So you see it as a while before that happens.
For the beamforming part of it in 5, yeah. But for basic like tracking, command and control, low bandwidth video, yeah, it's doable today. We do it all the time, multiple times a week, and it works fine. Yes, sir.
Is commercial aviation using any of this for their avoidance?
No, right now it's all ADS-B, as far as I know, and maybe they're starting to do some radar. I'm not sure, but yeah.
There's TCAS, but that's been around forever.
Yeah.
That's CDSB at the time.
Yeah.
Portions used.
And exponential, all kinds of different variations of radar.
Yeah.
Discussed. A lot of it is low, steep. We gotta move on to the next one. Good job.
Okay. Thank you. Oh yeah.